let us discuss another type of algorithms for graph learning, and these algorithms are based on random walk techniques, right. We know what is random walk. We discussed in chapter, I think, link analysis, link prediction chapters. So what is the idea here? The idea here is that we use random walk to capture the context of a node. Okay. So what happens if we have a sentence, right, in language, say I am going to my office, right, and if I ask you to collect the set of context words for the word going, you can say that I am to my office. These are the context words. In fact, the word going, let us say the word going appears in multiple sentences. Therefore, you basically look at 2 words before going, 2 words after going, and you accumulate all the words which appear around the word going, right. But in case of graph, right, context is very difficult to capture, right. As I mentioned earlier, graph does not have any unique structure. If we change the IDs of nodes, the entire thing will change, right. So what we do here, we use random walk to capture the context of nodes, right. So it captures the local neighborhood and structure of a node by performing enough random walks. We repeat random walks multiple times, in fact, from a given node and capture the context, right. And then why these methods are useful? Because these methods are fast, because you can run random walks from multiple nodes simultaneously, right. If a change occurs in a large network, that only affects those nodes around which the change has happened, right. So let us first understand what we are doing. Again, let me recap, right. So we are coming up for node u and node v. We are coming up with embeddings zu, zv, such that if node u and v are closer in the graph, zu and zv should be also closer, right. By the way, this part of the lecture is highly motivated by Ural Escobic's course on deep learning for graphs. So essentially the dot product zu zv transpose, okay, this should mimic the probability of u and v, right, co-occurring over random walk, meaning that if you start a random walk from u, what is the probability of encountering v? This should be captured using this one, right. So in other words, the probability that given a node u, you start your random walk r, you encounter v should be approximated by zu zv transpose, okay. So what we do here, we define a neighborhood, right, of node u using a random walk r. Let us say you have a network like this. You start an unbiased random walk from u, you move here, then you move here, and let us say the random walk size is 3, right. So you encounter this node, this node, this node in the first random walk. You repeat the random walk again, you may encounter again this node, then this node and this node. You again repeat the same process, you encounter say this node, then this node, right, and this node, and so on and so forth. So the length of the random walk is a hyperparameter, and the number of random walks that you want to perform is also hyperparameter. So, for every node you repeat multiple such random walks to collect its neighbors, the context, and you prepare a set. The set contains the nodes which are the neighbors of which are the neighbors or context of the given node u, right. And this set is a multi-set, remember this. Why this is a multi-set? Because here an entity can repeat. Say for example, this node can appear in multiple random walks. So, this entry, this node will appear multiple times in this set. This is multi-set. In general, when you talk about a set, the entities should be unique, but in multi-set the entities can be repeated. Okay. So, for every node u, I get a neighbor set, and what is the target? What is the target? That given this node u, let us say the embedding of this node is ZU, right. What is the probability that given this node you will see other nodes, all their neighbors? Probability given the embedding of a node which is unknown, what is the probability of its context nodes? This we want to estimate, this we want to maximize. Why? Because these are neighbor nodes, the closeness proximity should be higher for the neighbor nodes, right, given the target node, right. So, we want to maximize this. Instead of maximizing this, we essentially maximize the log. Okay. So, let me rewrite. We maximize the log of log likelihood, maximize the log likelihood given the source node u, you have target context nodes, right, using some random walk, right. And if we unfold it, remember this is a set, right, NRU is a multi-set, right. We can write it in this way, same as for every u we look at their neighbors, right, we look at its neighbors, log of v given, right. This is something that we maximize. Okay. Now, how do we calculate this one? Log of v given ZU. So, v is a node, v will also have an embedding ZV, right. So, what they proposed in the DeepWalk paper, what they proposed is that we can use shortmax kind of again operation, exponential of dot product ZU ZV transpose divided by summation of all nodes exponential of ZU Z in transpose. Okay. So, what is our final objective function? This is max. Okay. Generally we minimize, so maximize this one is same as minimize the negative of this. So, min, right, sum over all u present in the graph, sum over all of its neighbors minus log of this one exponential of right. You must have already understood the problem here. Okay, so what's the problem here? For every node, you have to calculate this one, the same as the one that we discussed in line, in graph, right? For every node, we need to calculate this sum over all the nodes. This is quadratic. This takes a lot of time. So what we do? We basically look at negative sampling. We apply negative sampling here, and then if we apply negative sampling, then this term would be approximated by log of remember, when we unfold it, this is log x by y, log x minus log y. So this is log x, log exponential will cancel out, right? But we really want to make it a probability kind of notion. Therefore, we replace exponential by a sigmoid, right? There is a paper which basically suggested this one. So sigmoid minus this part will be there, log of I basically sample k such nodes from the distribution PV. Okay, now I run this over all such k, log of sigmoid Zi transpose, okay, where I sample k such negative samples. Okay. So this is something that we want to, and along with this we have what else? No, I think this is the final objective function, right? And we want to minimize it. We have minus here. So this is DeepWalk. Okay. Couple of things to note: k, number of negative samples. What's the impact? If higher k value, your method would be more robust, right? At what happens is that k approximates all the nodes, right? Higher k also corresponds to higher bias towards negative sample. Therefore, we generally assign k to 5 to 20. K's value would be between 5 to 20. So this is DeepWalk. Okay. So the problem in DeepWalk is that it uses an unbiased random walk, right? Sometimes the problem in unbiased random walk is that you tend to capture only local context of a node. You may want to capture the global context as well. For example, say you have this structure, okay, this is U. If you only do random walk, it may happen that you will not encounter this node at all or this node at all, right? You would only restrict yourself within this part. But if you think about it, this node and this node, although they are far, their neighborhood structure is very same, right? Had it been a depth wise random walk, you could have also considered this node in your context. So after DeepWalk, there was another method proposed by Leskovic and team, which was called as node to Vect. Okay. So in node to Vect, the idea is that you bias your random walk to either confine itself within the local part or move to far apart from the node. Okay. And how do you do that? You do it using BFS and DFS, breadth first search and depth first search. If you are not aware of what is BFS, DFS, you can go back and look at some of the data structure courses. So, if you do BFS based random walk from this node, you should be able to capture these nodes. If you use DFS, you should be able to capture these nodes. Okay. So, we will use BFS and DFS in the random walk process and in the objective function as well. Okay. So, we captured the local and global context using BFS and DFS respectively, and to do so we define two parameters. One is called P, right. So, P is the return parameter, P is the return parameter, right, and you have Q which is called in out parameter. I will explain. Okay. So, what is the idea? Let us say you have a graph like this, okay, and this is, so let us say this is U, this is V, W, X, right, and let us say you have already started your random walk from U and you are currently at V. So, with the parameter, based on the parameter P, okay, based on the parameter P, you jump from V to U. So, return parameter, U is the source node. Based on the parameter, let us say you have another, based on the parameter Q, you decide to move further through this path or through this path, right, and right. So, what it is saying is, now this parameter P and Q, right, from this we basically calculate the probability. So, what we are saying is that when we have started our random walk from U and currently at V, with probability 1 by P, we come here to the seed node, with probability 1 by Q, we move there, with probability 1 by Q, we move there, and with probability 1, we come here. Why? Because think about it, V and W both are use first of neighbors. So, when we do BFS, you should be able to explore both V and W, right. Now, if you fix one parameter 1, then the other would vary accordingly. This is 1 by P. Okay. So, what does it mean? It means that if you decrease this P value, this probability will increase, right, meaning that you will encourage BFS. If you decrease Q, right, this will increase, meaning you encourage DFS, right. So, Q controls the in-out probability, in-out movement, and P controls the return kind of movement. Okay. So, this is the idea, right. Now, so this is called node to Vect. So, in the optimization function also, you basically incorporate, you make your, so this is your transition, right, this is your transition matrix, right, and as you see, this alpha is determined by this one, okay, and W is the weight, right. So, using this transition matrix, you basically run your random walk process, and using the random walk process, you will get inner U, the neighbors, right, and then you repeat the same process that we discussed in case of DeepWalk, right. So, the only difference is that you have a control on P and Q whether you want to do BFS or you want to do DFS, right. Now, look at this figure. So, this is a real world network, and you see here that if P equals to 1 and Q equals to 0.5 and P equals to 1, Q 0.2, Q2, right. So, what happens is that in this setting you are essentially capturing, right, you are essentially capturing different clusters because you are allowing you are allowed to move further because of this high because of this low high Q value, which is low 1 by Q, right, compared to this one, right. So, low 1 by Q basically prefers low 1 by Q, right, prefers what. So if Q is high, 1 by Q would be low, and low 1 by Q would not prefer DFS, right. Okay, and you see here in this case things like hubs, right, nodes with high degree, those nodes get prominent in this particular figure. So, this is about node to Vect and DeepWalk. These are very famous graph learning algorithms based on random walk, unsupervised methods, task independent methods, right, non-neural network based approaches. So, in the next lecture we will start deep learning based approaches for network embedding. We will discuss different GNN techniques, graph neural network techniques, GCN, graph attention network, graph sage, and so on. Okay, thank you.